we try to go on a path achieving thermonuclear fusion. The idea in fusion is that the hydrogen atoms then fuse into helium. They release a big amount of energy due to their together they are heavier than the helium, and to have to have it in a reactor and to use it for energy production, certain criteria have to be fulfilled. I will not bore you with the details, but there is a gain factor, and this gain factor says that at a critical and at a critical level, the confinement time and the density of the plasma gives two approaches: magnetical confinement, which to have a working power plant, and inertial confinement fusion, which increases the density of the target. Our aim goes in the direction of inertial confinement fusion. There are two types, direct and indirect type. Ours will be direct because we do not have we shoot the target directly with the laser. The most advanced type of fusion here is at the National Ignition Facility. They use an indirect drive. They shoot a gold nanotube with 192 or 992 laser beams, which then evaporates and produces X-rays, and the deuterium tritium ice is inside a shell. Earlier days there were plastic ablators. Nowadays they are using high density carbon, and as X-rays evaporate the shell, as the shell goes out, it compresses. Earlier days, the problem is that it is not a symmetrical compression, and this case results in Rayleigh-Taylor instabilities because the inner layer is more dense, and as you can see that they needed much more density. Later, the latest news in August, that they reached 1.3 megajoule kinetic energy. This was in 50 or something kilojoules, but they still have a burning time of 130 nanoseconds. We aim to minimize and actually to avoid the Rayleigh-Taylor instabilities, and this is a spin-off from heavy ion collisions, where in the quark-gluon plasma at the hadronization phase, the you can observe a time like oops, sorry, detonation. So the time like means that um, atoms are excited and energy is not given by the neighboring atom, but they get excited first by the laser beam, and then they ignite together independently from one another. So by the time the other laser beam reaches, they can ignite. At a constant absorptivity level, when the target has a constant absorptivity everywhere, then this time-like effect is very small. So 12% of the target ignites in this way. However, another idea came thanks to Kronorbert, who is working with nanoparticles, that we vary the absorptivity of the target depending, as we go inside the target, doping with nanoantennas, gold nanoantennas. These gold nanoantennas have the effect that they resonate, and they can at this resonation they can absorb more energy, and doping with gold nano rods, the absorptivity, as the absorptivity increases, it can be seen that this the amount of burning material would be around 73%. Our concept is to have two opposing laser beams and a cylindrical shaped target, laser beams coming from this direction, and to minimize the surface of the target. So we should have the minimum surface for a volume, and the deposited energy at a constant phase out. However, if we have an absorptivity that looks like this, it is a Gaussian-like shape, then the energy that can be deposited goes very deep inside the target. So since we have to achieve fusion, the particle in cell method was chosen. This is the method commonly used by physicists. The idea is that in a particle in cell method, on the cells we have the fields on the edge of the cells, and the particles move freely. This is a finite difference time domain method, which solves the Maxwell equation. So for earlier, we use this epoch code, which is written in C++, and this is the method that we calculate the fields in half steps. Then we have a particle pusher, which calculates the currents, and then we use that to calculate in the next half step the fields. So this is the particle have a shape, so they for the most simple one is triangle shape. 50% of the marker particle is inside the cell, and the other 50% of it is in the neighboring cells for one dimension. This is the first of the approximation, yeah, and so the nanorods finite difference time domain method. However, they cannot use they do not use electrons, so they cannot effects when the nanoparticles are below, for example, 20 nanometers. This the plasmonic effect which we use is the enhancement inside the target, so the energy absorption is enhanced. And in the classical case, the field solver, this gamma is a damping factor. In cell method, we can have the collisions. For example, in the epoch code, there is a built-in collision simulator, which is from Nambu and Perez. So the nanoplasmonic effect is due to the collective motion of the the conducting electrons. And for golden nanorods, for example, in vacuum, this empirical three-parameter equation was a result, and this and for example, this in vacuum, half of this wavelength is the resonant nanorods length at 25 nanometer diameter. So we simulated this inside the particle in cell with as we put also gold ions. Show you just a second the movie. Does it work? Okay, this doesn't. So then I will show. Actually, the movie shows the vibrations and also that the gold nanorod is shrinking because we have the electron spilling out, and this resulted in vacuum a 66 times higher and so in the conclusions, these models qualitative description of these nanorods. However, in future we will have to combine both approximations because the the absorptivity increases is slightly lower than the experimental results. We also would, this is also an approximation where the, we do not have for fields we calculate in spectral space, and this will be our next project because implementing in GPU the epoch code was slightly tougher. Load balance requirement. So the load balancing was very cleverly solved in the epoch. Thank you. Yes, sorry for that. The laser comes at 28 femtoseconds. It is a step function laser corrected with the cosine edges.
So that is the okay. In the simulation, you simulate electrons.
Electrons and yes, gold ions. And gold ions are so. And we have 3 times as many electrons.
Are these the ionization self-consistent, or do you assume an ion distribution?
We assume an ion distribution inside the region of the nanorod. So the number density outside of the nanorod goes to 0, and inside we have the number density of electrons of 10 to the 20 power of 28.
Plus
Yes.
Okay. So I can see this sense. So thank you very much, István.